Night fell over the Karoo while most of South Africa slept. On October 24, 2025 at 4:10 Universal Time Coordinated, Meerkat's 64 dishes faced a sliver of sky pressed close to the sun, a place few dare to listen. In the hiss of the radio band, two neat bytes appeared in the spectrum, 1,665 megahertz and 1,667 megahertz, textbook OH main lines. Not noise. Not a satellite. Not an instrument quirk. Chemistry speaking across hundreds of millions of kilometers. The source sat on a hyperbolic path through our neighborhood. 3 Atlas, Catalog CO 2025 I1, the third confirmed visitor from beyond the sun's hold. Months of tracking had pinned its orbit, speed, and brightening as perihelion neared on October 29th. No one had ever logged radio from an interstellar object. From Jansky's first Milky Way static to the present, nothing. Until this morning. OH means water torn by ultraviolet light. H flies off. OH lingers and imprints razor-thin absorption at those precise frequencies. See those lines and you infer H2O. See them from a body born around another star and you glimpse a chemistry we share with far places. Skeptics did what skeptics do. Interference checks. Satellite passes. RFI catalogs. Cross-checks with failed attempts on September the 20th and 28th. Silence on both dates. Why now? Geometry and timing. On the 24th, the object sat 3.76 degrees from the sun, a punishing place to observe, yet motion was a gift. A line of sight velocity near minus 5.66 km IS Doppler shifted OH away from solar raw, sliding the lines into a quieter slice of L-band. Line widths near 0.9 to 1.3 km IS stayed steady across scans. If this were junk, widths would sprawl, centers would wander. They did not. The signal rode exactly where the ephemeris said the target Saturday. Earlier tries failed because the ice was sleeping. Late September meant low heating, low sublimation. By late October, days from perihelion, the nucleus warmed, the coma swelled, and OH filled a column thick enough to drink starlight at 1665 or 1667 megahertz. The window was thin. Too early, no gas. Too late, solar conjunction buries the target in radio glare. The 24th was the slot. One detail unsettled nerves. The sky position was within about 9 degrees of the 1977 WOW event, a region in Sagittarius that once lit a narrowband spike strong enough for Jerry Ehrman to circle in red ink. No one claimed a greeting now. OH absorption is a shadow, not a broadcast. Even so, proximity to law stirred a wave of proposals, posts, and headlines while teams kept measuring. From that point forward, a sharper question set the tone. When the cosmos whispers, how do we tell physics from intent? Nature makes lines. Intelligence encodes structure. Sometimes the border blurs. 3 Atlas did more than whisper. It behaved oddly. Observers logged 8 anomalies as perihelion approached. Tail kinematics that swayed more than models predict. Brightness swings near half a magnitude across a week, off-axis jets likely fed by subsurface pockets, and an antitail mirroring the main tail in brightness and reach. Antitails can be perspective tricks near the orbital plane. Yet the symmetry here stood out. A fast rotation or elongated body could drive it. Jets near opposite poles would fit too. The pattern demanded better data, not leaps. The orbit raised eyebrows as well. Instead of a steep dip through the ecliptic, the approach ran nearly along it. With only 3 interstellar cases on record, 1 I Oumuamua, 2 I Borisov, and now 3 I Atlas, statistics are thin, but alignment with the planet's plane is a curious roll of the dice. Some hinted at local origin from a system whose plane matches ours. Others flagged small number bias. The safe call, interesting, not decisive. What did the spectrum say? Nothing coded. No narrowband needle, no pulse train, no phase tricks. A clean OH absorption pair with proper ratios, widths set by thermal and turbulent motion in a tenuous coma. Centers where Doppler math predicts. In SETI terms, this sits on the natural end of the continuum. Yet its importance lands elsewhere. First direct radiochemistry from alien ice, No dust catcher required, no flyby needed. The universe delivered a sample. We listened. Cue the larger frame. Oumuamua in 2017, non-gravitational acceleration and no visible coma. Puzzles stacked on puzzles. 2I Borisov in 2019, a normal comet by every metric, water, CO, CN, a dusty tail, comfortingly familiar. 3 Atlas splits the difference, unmistakable cometary gas with quirks that don't fit a neat template, and now the first radio detection from an interstellar object. A new channel for a class we barely know. Maycat's L-band reach made this possible. 64 dishes over 8 kilometers form a sharp ear in protected, radio-quiet desert. The correlator fuses streams, mutes RFI, and resolves lines narrow enough for molecule-by-molecule inference. SARAO's pipeline flagged, humans inspected, checks passed. If the team had tried 2 days later, the sun's geometry likely would have smothered the attempt. One morning, one slot. From here, the story widens into how and where to hunt signals of technology without intent. Not beacons, not math carved into a carrier, but side effects, industrial byproducts, exhaust chemistry, isotopic oddities, signatures that leak. Earth leaks. A shell of radio and radar expands near light speed, a messy stamp of civilization. A distant ear would not see a single tone. It would see chaos with telltale structure. In spaceflight scenarios, engineered volatiles or fine-tuned outgassing might sculpt spectra and dynamics in ways that look natural until statistics say otherwise. Distinguishing such traces from physics demands libraries of normal, big samples, and algorithms trained to spot outliers buried in line forests. Replication efforts spun up fast. Green Bank's 100-meter dish, Fast's 500-meter ball, and the VLA offer complementary sensitivity and spatial filtering. Geometry was the obstacle. The source dipped behind the sun fast. 2 earlier blank runs underscored variability. Activity rises with heating, rotation gates the release, viewing angles bias the column. Without continuous coverage, gaps stay gaps. Underneath the speculation sat a grounded outcome. The OH lines prove water vapor broke under UV from a body born around another star. Rosetta's 67P taught us how such chemistry plays out nearby. Swift's UV data tied to 3 Atlas traced water production weeks in advance. Combine UV, optical, IR, and radio and a multi-wavelength portrait appears. Temperature near 230 K during the detection window. Cold by habit, ideal for steady sublimation. Gas flow that builds a coma and tail without blowing the nucleus apart. Selective volatiles where the most fragile species likely weathered away during long interstellar winters, leaving water to dominate near the sun. From there, the mind drifts to panspermia in its modest form. Not cells crossing gulfs, but ingredients. Laboratory ice under UV and cosmic ray analogs yields amino acids and simple organics. Meteorites carry similar cargo. Scatter trillions of icy bodies between stars over eons, and every system receives a drizzle of chemistry. 3 Atlas slots in as array direct confirmation. Extrasolar ice releases familiar molecules under familiar light. The maneuvering idea made headlines too. Use sublimation as thrust, mask a probe as a comet. Physics permits gasjet pushes. In fact, comets do it constantly without any design. Perihelion is the right place for small velocity changes with big trajectory effects. During this pass, minor deviations stayed within non-gravitational terms explained by asymmetric jets. No exotic accelerations emerged, no spectral hints of odd propellants, no need to invent control systems. Fun to debate, unnecessary to fit the data. All this folds into a quiet shift within SETI. The classic play, seek ultranarrowband spikes, remains clean and testable. Frank Drake's first campaign at Tau Ceti and Epsilon Eridani set the template, and modern arrays keep scanning. Decades in, the tally of repeating, structured beacons sits at 0. That does not end the search. It broadens it. Chemistry, dynamics, waste heat, time-variable spectra, odd isotopes, each offers a lane. 3 Atlas shows radiochemistry works on interstellar ice. Next time, teams will watch more lines at once, compare ratios, and look for timing patterns no comet physics predicts. New hardware strengthens that plan. ESO's foremost came online in October with robotic fibers capturing spectra for 2,400 targets per shot, an assembly line for composition. Feed it small bodies, stars, and transients, and a chemical atlas grows. The Vera C. Rubin Observatory will take the baton next, a 10-year movie of the sky, imaging the visible dome every few nights. Expect millions of new asteroids, a flood of Kuiper Belt bodies, and, importantly, early alerts for interstellar visitors months before perihelion. With time to plan, radio arrays can camp on promising targets through the full heating curve instead of stealing a single morning near the sun. Machine learning pipelines will triage motion, flag hyperbolic tracks, and summon follow-ups within hours. The neighborhood around Earth keeps surprising us too. Quasi-satellites like 2025 PN7, looping in a tilted, loose dance near our orbit, remind us how messy three-body dynamics can be. Such niches even spark cloak-and-watch thought experiments. Park a small, rock-like observer in a resonant path and linger for decades. Reality likely gives us plain stones, but the exercise clarifies how subtlety hides in plain sight. Step outward again and precision listening reveals other patterns. Pulsar timing arrays have found correlated drifts, space-time breathing on year-to-decade timescales, most likely the background from supermassive black hole binaries. Alternative ideas invoke exotic dark sector fields. Either way, the method rhymes with spectroscopy. Track tiny shifts in frequency and phase, pull meaning from noise, and let statistics speak. The same discipline that plucks OH from a bright radio sky is the discipline that hears gravity's baseline across the galaxy. At the far end of scale, JWST now maps heat and molecules on worlds many light-years away. Phase curves of WASP-18b reveal winds, hotspots, and chemical structure on a planet glowing like a forge. The logic matches comet work, light split to lines, lines tied to species, species tied to temperature, pressure, and flow. One toolkit, many frontos. Why does this leave 3 Atlas? With a sober claim and a broad consequence. Sober claim: MEERKAT captured the first radio OH absorption from an interstellar object, consistent with water chemistry in a sun-warmed coma. Broad consequence: radio spectroscopy now joins the toolkit for studying material born around other stars, in real time, from the ground. Stack events across the next decade: Rubin's early notices, 4MOSD's multiplexed spectra, JWST's IR, MEERKAT fast VLA in L-band, and a statistics-rich picture of visiting ice will form. Composition ranges, activity onsets, tail dynamics, isotopes, when reachable. Outliers will pop. Most will fold neatly into physics, a few may force new ideas. If anything pushes toward engineered signatures, it will be regularity where thermal chaos should rule, ratios too precise across epochs, or trajectories that cluster in ways random scatter does not. The cultural beat runs in parallel. People want contact. Headlines bend words until alien chemistry reads like alien chat. Patience is hard, yet the deeper story is not a letdown. It is origin science in action. Water breaks under starlight the same way here and there. OH absorbs at the same frequencies here and there. A comet from elsewhere behaves enough like ours to let us read it. That unity is the point. When the signal faded as the object slid behind the sun, the moment closed. 3 Atlas now races outward near 42 kilometers per second, bound for a future star we will never see. We had one clean shot. We took it. The spectrum carried 2 sharp hollows where OH drank the background, line centers where Doppler math said they belong, widths that told us the gas was thin and moving as expected. For the first time in human history, we heard water from another system with a radio ear and found it indistinguishable from our own. The next visitor will arrive with little warning, then many more once Rubin starts its sweep. Each one will add a data point to a map of galactic chemistry drawn by wanderers. Some will be plain, some will be tricky, a ray few may refuse to fit. And through all of it, our job stays simple and hard. Aim on time, split the light, measure without bias, compare across methods, and let patterns emerge. Maybe the cosmos never meant to say anything to us. It speaks anyway, through molecules that form and fall apart, through orbits carved by gravity, through temperatures etched in spectra, through waves that stretch distance itself. 3 Atlas did not send a message. It carried one written in the oldest ink we know, water under a star. We listened. We understood enough to know where to keep looking. We listened, and what we heard was not a message in language, but a pattern in chemistry, a rhythm older than Earth itself. When hydroxyl radicals spoke through those twin absorption lines, they told us the same story water has told since the dawn of the cosmos. A story of light-breaking bonds, of heat awakening frozen matter, of molecules wandering between stars, carrying fragments of potential life. As 3 Atlas slipped past the sun, its trail thickened with gas and dust, a luminous haze shedding what had been sealed in darkness for millions of years. Each molecule released was a memory, of the star that birthed it, of the collisions that flung it free, of the cold eternity that followed. And now, briefly, those memories crossed paths with our instruments and left traces on our data. When the radio signal faded, astronomers around the world scrambled to preserve every byte. Copies were sent to archives in South Africa, Europe, and the United States. Simulations ran overnight. Some modeled the outgassing jets, trying to reproduce the twin tails and the slight orbital shift. Others analyzed the frequency domain, calculating optical depths, column densities, and excitation temperatures. The verdict: the lines matched theoretical profiles for thermalized hydroxyl at roughly 200 Kelvin. No modulation, no drift, no hidden harmonics. Nature, pure and simple. But nature doing something we had never seen from another star's debris before. For days, observatories chased the comet across dawn skies. Optical telescopes tracked its brightness, noting periodic flickers that hinted at rotation. Infrared instruments tried to measure thermal emission, though the sun's glare made it difficult. The ultraviolet spectrum, captured by SWIFT, showed traces of molecular hydrogen and faint carbon monoxide. Everything pointed to one conclusion: an ordinary comet by composition, extraordinary by origin. News spread quickly. Some headlines were cautious: interstellar comet reveals water signature. Others leaned toward sensation: alien object sends radio signal. Forums filled with speculation. Was this proof of panspermia? Could it be a probe? Was the proximity to the WOW signal more than coincidence? In truth, nobody knew. But for a few days, the world looked up again, united by curiosity instead of fear. Inside laboratories, researchers revisited old data from 1I Oumuamua and 2I Borisov. Could they have missed faint radio lines? Could subtle hydroxyl absorption have been buried in noise? Retrospective analyses turned up nothing conclusive. Those objects had been quieter, or we had been less ready to hear them. Meerkat's sensitivity, its clean location, and the improbable geometry of 3 Atlas had aligned perfectly, a 1 in a million shot. That's what made the moment sacred to scientists. The right conditions, once, and we caught it. Beyond the excitement, the discovery forced a philosophical reckoning. For decades, SETI had focused on deliberate broadcasts, narrowband beacons, pulse trains, clear mathematical signatures. But what if intelligence rarely speaks in our terms? What if the true markers of civilization lie in subtle irregularities, waste heat, chemical residues, artificial isotopes drifting through space? Maybe the proof of life advanced enough to shape its environment won't come as a radio greeting, but as pollution, as order where chaos should rule, as symmetry born from control. 3 Atlas taught us the value of context. Chemistry itself can be a message, not one encoded by will, but by consequence. The universe writes its autobiography in molecules, in photons, in trajectories. To read it, we need patience and pattern recognition, not expectation of dialogue. While astronomers debated, other discoveries unfolded. 2025 PN7, Earth's tilted quasi-satellite, entered the story, a rock looping around the planet's orbit at a 40-degree inclination. It never strays too far, never draws too close. Some called it Earth's secret second moon. Others saw it as a reminder that the solar system is alive with motion more complex than textbooks suggest. In a way, PN7 mirrored 3 Atlas, another traveler caught between gravitational hands, another symbol of how space is less empty than we think. Quasi-satellites like PN7 come and go, lingering for decades before slipping away. One can almost imagine one of them harboring something more, a dormant probe, a silent witness, a listener waiting. It's speculation, yes, but the mere fact that such stable orbits exist makes the idea not impossible. Astronomy breeds humility. Every time we declare a region of space empty, new instruments prove us wrong. That's the real undercurrent of 2025, a year of seeing what we couldn't before. The European Southern Observatory's foremost telescope came online, an engine of spectra, capturing thousands of chemical fingerprints each night. The Vera C. Rubin Observatory prepared to map the entire visible sky every few nights, a time-lapse of motion and change. MeerKAT continued to refine its listening, and its successor, the Square Kilometre Array, waited in the wings, promising sensitivity orders of magnitude greater. Together, these machines form a nervous system for humanity's perception of the cosmos. Billions of data points, each one a neuron firing with light from another place, another time. When the Rubin Observatory begins its survey, it will find new interstellar visitors by the dozen. Not once a decade, but regularly. Objects like 3 Atlas will become common data, no longer singular miracles but nodes in a growing statistical web. From their velocities and compositions, we'll build models of how matter circulates between stars, how one system's loss becomes another's gain. In that exchange lies a truth deeper than any one discovery. The galaxy is porous. Material, and maybe information, flows continuously across it. Every star system participates in this quiet trade. Yet the flood of data will bring a new challenge: interpretation. As detections multiply, subtle outliers will blur into noise. Artificiality, if it hides anywhere, may masquerade as routine anomaly. That's why machine learning, pattern recognition, and cross-spectral analysis will matter as much as telescopes themselves. We'll need algorithms to think the unthinkable, to notice correlations our biases would dismiss. By the end of 2025, MeerKAT's hydroxyl detection still stood alone, but it had changed the game. SETI researchers began discussing chemotargeting, using known chemical signatures as search markers for intelligent activity. Instead of waiting for a beacon, we'll listen for impossible ratios, for molecules that shouldn't coexist, for line strengths that defy thermal models. The universe may not shout, but it might leave fingerprints if we learn how to see them. Meanwhile, deeper forces ripple through spacetime itself. Pulsar timing arrays, listening to millisecond pulsars scattered across the galaxy, have found a low-frequency hum, gravitational waves from titanic black hole binaries, or perhaps the tremor of dark matter fields. Whatever their origin, they confirm that even the fabric of reality vibrates. Space stretches and compresses like a breathing organism. These waves sweep through everything: planets, comets, us, and felt, but real. Perhaps they even nudge objects like 3 Atlas in imperceptible ways over eons, shaping trajectories we read as random. The cosmos, it seems, has a pulse. And while radio telescopes listened to that pulse, the James Webb Space Telescope turned its infrared gaze on distant worlds. In November 2025, it mapped the atmosphere of WASP-18b in 3 dimensions, a gas giant orbiting so close to its star that its year lasts less than a day. One side eternal noon, the other endless night. The data revealed winds faster than sound, metals vaporized into plasma, water torn apart and reassembled each orbit. In those alien skies, chemistry and violence danced together. The same quantum rules that define hydroxyl on a comet also sculpt the climate of a planet 10 light-years away. The scale changes, the physics does not. These threads, radiochemistry, exoplanet atmospheres, gravitational murmurs, optical surveys, converge on a single truth. We are learning to read the universe in full spectrum. Every wavelength is a letter, every measurement, a sentence. Together, they form a story about origins, persistence, and possibility. Consider what this means for the oldest question. Are we alone? 3 Atlas did not answer it, but it reframed it. If water and organics travel freely between stars, then life's ingredients are universal. The emergence of life may not require miracles, only time and stability. Yet if that's true, why the silence? Perhaps civilizations seldom survive long enough to overlap. Or perhaps they never needed to shout. Maybe intelligence, once it matures, speaks through balance instead of broadcast, through stability, not noise. Maybe the truest expression of awareness in the cosmos is subtlety. In that sense, the hydroxyl lines could be the faintest whisper of something grander, not of other minds, but of the cosmos itself, communicating through the language of physics. Each molecule, each photon, a syllable in a message that says, "This is what I am, this is what I make, this is how I endure." As 2026 looms, humanity stands at a threshold. Rubin will soon reveal the solar system as a shifting mosaic. Foremost will drown us in spectra. MACAT will keep its vigil. FAST, Green Bank, and VLA will join it, listening for the next alien chemistry, the next flicker that says water elsewhere. Our detectors are tuned. Our algorithms are hungry. The sky is alive with information, and for the first time, we have the tools to keep up. 3 Atlas is gone now, receding into darkness at 42 kilometers per second. It will wander between the stars for another million years before it crosses into some new system, perhaps to be seen by another set of eyes, another species asking the same questions we ask tonight. It carries within it the memory of our observation, not consciously, but physically, as altered dust, as molecules shifted by sunlight. For a brief moment, our two civilizations, ours of flesh and thought, and its of ice and orbit, intersected. We left fingerprints on each other. One day, another visitor will come. It will glitter faintly against the background stars, and somewhere, a telescope will notice its movement. Within hours, databases will hum, alerts will go out, and across the planet, instruments will turn to listen. Maybe it will bear carbon chains more complex than any seen before. Maybe its isotopes will hint at unknown processes. Or maybe, hidden in the harmony of its spectrum, we'll find a pattern that doesn't belong to randomness at all. Until then, we listen. The airwaves between stars are quiet, but not empty. Every comet that hisses as it warms, every pulsar that ticks, every planet that glows, adds a note to the universal chorus. 3 Atlas was one of those notes, faint, transient, perfect. A drop of chemistry carrying the echo of creation. Maybe that's all the cosmos ever meant to tell us. That we are part of the same process. That life, matter, and starlight are variations of one theme. That the universe doesn't need to speak in words when everything within it already says enough. And as the signal from 3 Atlas fades into archival noise, what remains is not silence, but invitation. The next signal, the next anomaly, the next flash of data could already be inbound, crossing the void toward our waiting antennas. When it arrives, we'll be ready to measure, to question, to wonder, and to listen once more for the chemistry of life, whispering beneath the noise of the stars. When the signal from 3 Atlas faded into the quiet hum of background radiation, it left behind a strange kind of silence, not the absence of sound, but the charged stillness that follows revelation. In that pause, humanity recognized something subtle but profound. For the first time, we had confirmed that water, the molecule that writes the code of biology, moves freely between stars. The significance wasn't about aliens or mystery. It was about connection. A thread running through the galaxy that ties together the birth of stars, the death of worlds, and the chemistry of life itself. The detection reshaped the way we think about exploration. Until that point, interstellar research had been reactive. We waited for visitors, spotted them by chance, and scrambled to study them before they vanished. But 3 Atlas showed that we could do more than observe. We could anticipate, coordinate, and extract meaning from fleeting phenomena. It proved that the frontier wasn't distance anymore, it was interpretation. Understanding had become the new exploration. In the months that followed, data scientists and astronomers built what they called the Atlas Framework. It was a shared platform for processing spectral data across instruments: MeerKAT, FAST, Green Bank, ALMA, Foremost, JWST, and soon, Rubin. Every frequency observation, every spectral anomaly, every transient event would feed into the network. The goal was simple: to let machines notice what humans might miss. The first generation of algorithms had been good at sorting known signals from noise. The new generation would look for structure, patterns too faint, too slow, or too irregular for the human eye. The framework began with hydroxyl, using the Atlas detection as a benchmark. Scientists simulated thousands of hypothetical comets, each with different compositions, temperatures, and orbital geometries. They mapped how OH lines shift, broaden, and blend under various conditions. Then they added noise, interference, atmospheric absorption, instrumental drift, and trained the algorithms to tell real chemistry from artifacts. By early 2026, the system could flag an anomalous spectral feature within seconds of capture. What once took weeks of human verification now happened automatically. It didn't take long for the first surprise. In February, MeerKAT picked up a weak hydroxyl line from another comet, CO 2026b2, a native solar system object. The line profile looked almost identical to 3 Atlas, same central frequency, same width. But the ratio between the 1665 and 1667 MHz lines was off by 2.3%. It was a tiny difference, barely outside error margins, but real. In a meeting at Sarajevo, one researcher called it the Atlas Echo. Not alien, not artificial, but proof that our instruments were now sensitive enough to see the subtleties of cometary chemistry, to map variations in excitation and density on scales we couldn't before. The algorithms caught more: hydroxyl in unexpected places, faint traces near inactive asteroids, weak emissions in regions where no comets should be. Some were later dismissed as reflections or background contamination. Others remained unexplained. Patterns began to form: clusters of detections near the ecliptic, patches of sky where signals seemed to come and go. Scientists debated whether these were echoes of interstellar debris trails, chemical clouds left behind by passing objects, or simply coincidence. No one was sure. What mattered was that we were listening differently now. Every signal, even a false alarm, became a data point in a larger map of the unknown. At the same time, the Vera C. Rubin Observatory was ramping up. Its first full sky passes began in May 2026. Within weeks, it discovered more than 40,000 new small bodies, asteroids, comets, and faint transients, and among them, one stood out. Designated CO 2026 G1 Serpens, its orbit was unmistakably hyperbolic. Another interstellar object, barely detected in the optical band, moving fast enough to escape the sun's pull forever. Its perihelion was 6 months away. This time, the world was ready. Observatories across continents locked onto it. MeerKAT began radio surveillance. Foremost prepared spectroscopic campaigns. JWST scheduled infrared time. Even amateur astronomers joined the global coordination effort, tracking the faint speck as it approached. The lessons of 3 Atlas guided everything: observe early, observe wide, and compare across wavelengths. By August, Serpens was bright enough for detailed spectra. It revealed something unexpected. Instead of water vapor dominating the outgassing, the primary signature was formamide NH2, a complex organic molecule and a known precursor to amino acids. Its detection wasn't shocking on its own. Formamide exists in molecular clouds and comets alike, but its abundance ratio was startling. 10 times higher than typical solar system comets. Enough to raise questions about the environment where it formed. The discovery revived interest in the idea of panspermia, not as myth, but as mechanism. If interstellar objects routinely carry molecules like formamide, glycine, and acetonitrile, then every planetary system in the galaxy might share the same chemical seeds. Life could be a recurring event, not an anomaly. Each star would be a lab, each comet, a courier. By late 2026, As serpents curved around the sun, the coordinated observation effort became a model for how humanity could study interstellar phenomena. The event generated petabytes of data. Every second of exposure across multiple instruments was logged, time-stamped, and cross-correlated. The spectral analysis alone took months. In the end, Serpens confirmed what 3 Atlas had hinted at. Interstellar chemistry is familiar. Not alien in the cinematic sense, but alien in scale. The same molecules, just moving between stars, carried by time and gravity. Meanwhile, other branches of astronomy pushed the boundary of detection itself. Pulsar timing arrays refined their models, confirming a stochastic background consistent with gravitational waves from merging supermassive black holes. Yet residuals remained. Tiny, unexplained deviations, systematic, correlated, but not matching any known gravitational signature. Some speculated they might be caused by oscillating dark matter fields. Others suggested they were artifacts of solar-wind interactions or calibration noise. But the coincidence fascinated theorists. The patterns seemed to fluctuate with the same multi-year periodicity as the observed brightness variations in certain comets. Probably coincidence. Still, curiosity turned it into data. Back in the optical domain, the Foremost survey had begun to build the largest chemical atlas of the Milky Way ever compiled. Millions of stellar spectra now traced the galaxy's evolution, element by element. From this data, scientists constructed a chemical topography, a 3D map showing where elements like oxygen, carbon, and nitrogen concentrated over billions of years. The picture that emerged was one of immense dynamism. Elements didn't stay put. They flowed across arms and orbits, recycled through supernovae and accretion disks. Every star's composition was a record of everything that came before. And this realization brought another shift. 3 Atlas wasn't rare. It was inevitable. Interstellar objects weren't intruders. They were migrants, pieces of an ongoing galactic circulation. The universe isn't a static sculpture. It's a living network of exchange, where every system borrows from its neighbors. In that view, panspermia wasn't speculation. It was structure. But the philosophical implications ran deeper still. If matter and chemistry flow so freely, then perhaps intelligence is part of the same current. Not in the sense of civilizations crossing space in ships, but in how complexity itself propagates. Maybe intelligence isn't localized. Maybe it's emergent, a pattern that appears whenever matter becomes sufficiently organized and fades when conditions change. Maybe it has no origin and no end, only instances. And if that's true, then our search for extraterrestrial life might be a misunderstanding of what life means. Perhaps the universe is already alive, not in metaphor, but in mechanism, self-organizing, self-recording, aware only through the things that compose it. The chemistry of 3 Atlas might not just be a relic of alien systems. It could be a symptom of a living cosmos, one that evolves through feedback and resonance. This was not mysticism, though it sounded close. It was the scientific recognition of pattern. Every discovery, from hydroxyl lines to pulsar hums, hinted at a unity underlying apparent randomness. The more precisely we measured, the more coherence we found. As 2027 dawned, the Atlas framework matured into something larger. It became the backbone of Synapse, a cross-disciplinary program linking astrophysics, chemistry, AI, and philosophy of science. Its mission was to map correlations across scales, from molecular lines in comets to gravitational distortions across galaxies. It treated the universe like a single data set, an unfolding computation. MACAT fed it radio spectra. Rubin supplied orbital data. JWST added infrared signatures. LIGO and NANO-GRAVE contributed timing streams. Out of this torrent, Synapse sought emergent order, connections that no human intuition could trace unaided. In one of its first public reports, Synapse published a visualization, a 3D map showing every detected spectral feature of hydroxyl, carbon monoxide, and formamide across hundreds of comets, nebulae, and interstellar objects. The display looked like a neural network, filaments branching, clusters glowing, connections shimmering across the galactic plane. It wasn't proof of consciousness, of course. But it made people wonder. The cosmos, rendered as data, looked uncannily like the structure of a brain. Meanwhile, telescopes continued to work quietly. MACAT upgraded its receivers. FAST installed cryogenic amplifiers that doubled its sensitivity. ALMA tuned its dishes to look for complex organics in star-forming regions. And Rubin kept sweeping the sky, discovering 2 more interstellar objects before the year ended. One of them, CR 2027 Q1 Kairos, carried traces of cyanamide and acetic acid, both precursors for nuclear-based chemistry. The detection came from JWST's infrared data, but the key confirmation came from ground-based radio. The lines were faint, but there. Humanity had, for the second time, heard the chemistry of life drifting through space. By now, the world no longer greeted such news with disbelief. It had become rhythm, detection, confirmation, catalog, debate. But beneath the routine, something was shifting. Our perception of isolation was breaking down. The stars were no longer unreachable points of light. They were connected to us by rivers of matter and frequency, by molecules older than any living thing on Earth. And yet, the silence of intention remained. No beacons, no messages, no proof of others who look back. Only chemistry, only physics, only structure. Some found that comforting, others found it unbearable. But perhaps the distinction no longer mattered. Because even if intelligence elsewhere never sends a signal, the universe itself has always been speaking, through the order of its laws, through the persistence of pattern, through the recurrence of life's ingredients wherever we look. So we keep listening. Every telescope pointed skyward, every detector humming in the dark, every algorithm sorting through noise, all of them part of the same act of attention. The act of asking. The act of being aware enough to wonder. Somewhere, far beyond the reach of our senses, 3 Atlas continues its journey. It carries traces of us now, the sunlight reflected from our planet, the radio waves we use to study it, perhaps even fragments of its own spectrum imprinted in the data streams we broadcast across the sky. It will drift for 1,000,000 years, until some other star's gravity slows it, warms it, and wakes its chemistry again. Maybe another species will listen. Maybe they'll detect the same hydroxyl lines and wonder, as we do, whether water speaks the same way everywhere. And when they do, maybe they'll realize what we're starting to understand. That the universe doesn't need to say hello. It already has. Every molecule is a word. Every photon a sentence. And together, they form a story that has no author, only readers bold enough to listen.